Hi everyone. Today we have another instance of our ZX seminar, and we will have Robert Booth who will be talking about his recent work with Titouan, Carette, and Comfort on graphical reasoning for Gaussian quantum mechanics. Please, Robert.
Yeah, thanks. So this is a talk just based on an article we recently put on arXiv. Maybe Cole can stick that link in the chat for me. I haven't actually got it ready. It's a work I'm really quite excited about, something I've been thinking about for a long time. I think Titouan and I first started thinking about this kind of thing back at the start of our PhDs in 2018 and made very little progress on the problem at the time. So I'm really happy now that I actually have something to say about this problem all of these years later. I'm actually going to present this via a detour through the finite dimensional stabilizer theory, because actually the way we design this language bears a lot of similarities to that case, and in particular the graphical language that I gave a talk about a couple of months ago now, maybe, on graphical symplectic algebra, which is another recent work that we completed with Titouan and Cole. And in particular, I'm going to look at the stabilizer theory in odd prime dimensions, because in that case, I mean, for those of you who've seen my previous talks, I've been going on and on about this for ages, but in that case, the stabilizer theory is particularly nice. So let's have a reminder on the stabilizer formalism for finite dimensional quantum systems. In finite dimensional quantum systems, we have a vector space which is generated by vectors of the form from 0 to d minus 1. So we have a d-dimensional Hilbert space. And in fact, I'm typically going to label these things as the group of addition modulo d. And really, the reason why I only work in odd prime dimensions is because in that case, the group of integers with addition mod d has multiplication mod d, and arithmetic mod d in that case actually gives you a field structure, which is the finite field with p elements, or odd prime number of elements. From this, sort of acting on this space, we can define a sort of generalization, straightforward generalization of the Pauli group, where the X gate acts here as translation through your basis elements. And then the Z gate is slightly more subtle to define, but as in the cubic case, where the Z gate acts as multiplication by plus or minus 1, here the Z gate acts as multiplication by a pth root of unity. This thing is a pth root of unity. And so then, given these two X and Z operators, we define a Pauli operator to be any unitary operator which we can generate by applying these two things, and also their generalization to sort of multi-qubit. So where I have a tensor product of these things acting on multiple quantum systems at the same time. Now, in the stabilizer theory, we don't want to think about quantum states as vectors in a Hilbert space. Instead, the stabilizer theory says that there's a fairly large class of interesting quantum states that we can characterize uniquely following this definition at the bottom of the screen. And what we want is, we ask for an abelian subgroup S of the Pauli group acting on some number of quantum systems. And if this abelian subgroup of the Pauli operators is maximal, then in fact it determines a unique pure quantum state via the following equation down here. That is, every element of this maximal abelian subgroup stabilizes the state S. And so we'll call the subgroup S the stabilizer group of the stabilizer state S and vice versa. Now, this is a nice definition. It's very useful. A lot of things have been worked out in the stabilizer theory, thinking about these things group theoretically. But really, a lot of the time, and in fact, even in a lot of the articles that use stabilizer subgroups, they are thought of more as vector spaces rather than subgroups. And I'll explain how that works. So if I take a pair of Pauli operators, let's call them XCZD, then I can encode the commutation relation. I can calculate the commutation relation for these things. And in fact, you will find that you end up with something like this: AD minus BC times XCZD XAZB. And so really all Pauli operators commute up to a phase which is determined by, so this is in, say, the one quantum system or the one qubit case, is determined by a phase which is really just determined by this this form, or this simple function of the labels or the parameters of my Pauli operators. And in fact, you can generalize this quite straightforwardly to the n sort of n qubit case by instead asking that here I have inner products. And the two Paulis here that I have will commute precisely when this this form is equal to 0. So this gives me a couple of things. First, I have an association to each element of my finite field FP squared, where here this sort of, oops, the element that I'm mapping up to the top is going to be the element AB, is associated to a Pauli. And then I have a map, omega FP squared times FP squared, or in general 2 to the n if I'm looking at n qubit Pauli operators into FP, which is simply calculated following this equation up here. Now this thing here is called a symplectic form. And the pair which consists of my vector space FP2 to the n and the notion of a symplectic, for the data of a symplectic form on that vector space is called a symplectic vector space. And if you do some simple if you do some simple linear algebra, or some simple algebra manipulating these things, it's not too hard to convince yourself that if I have maybe I can do something like this and have both things on screen at the same time. If I have a stabilizer group S in my Paulis, then the collection of pairs here AB in my vector space FP2 to the n that correspond to each of the elements of my stabilizer group S are going to form a linear, or I suppose a subspace of a space of fp2 to the n. And because of the fact that the operators in S have to commute, remember we imposed that stabilizer groups are abelian subgroups of the Pauli. We know that we must have the symplectic form must vanish on this subspace corresponding to the stabilizer group S. So this kind of subspace here is called an isotropic subspace of my symplectic vector space. And if you impose furthermore that you want it to be maximal isotropic, just as we imposed that stabilizer groups are actually for states are maximal abelian subgroups, then the corresponding what people in symplectic linear algebra and symplectic geometry call these subspaces are Lagrangian subspaces of the symplectic vector space. And so what this means is that we've set up a sort of sequence of isomorphisms between some class of quantum states, which are usually called Clifford quantum states, these stabilizer subgroups of the Pauli operators, and I suppose I didn't need to redraw this, these Lagrangian subspaces of the symplectic vector space, which is this one, of fp2 to the n omega, where here these are quantum states on n cupids. And this is stabilizer subgroups of the Pauli operators acting on n cupids. But in fact, you can take this analogy quite a lot further. We can actually capture a lot more of the stabilizer theory in the symplectic picture. So if you want to ask yourself now, I have a stabilizer state, I want to do some kind of quantum operation acting on this state, such that I'm preserving the fact that I'm mapping it still within the stabilizer fragment. So I'm only allowed to map stabilizer states to other stabilizer states. And you could ask what kind of unitaries, it's a natural question to ask what kind of unitaries, therefore, are going to do this. And the right definition here is this notion of Clifford group, which is really defined by this property here. That is, a unitary U here belongs to the Clifford group if and only if for all Pauli's P, the conjugation of P by my Clifford element is still a Pauli operator. And this guarantees that in the stabilizer subgroup picture, when I conjugate every element of my stabilizer group by U, this is still going to be a stabilizer group of potentially a different state, but still stabilizer. Oh, in fact, I've written it down here. Now, it turns out that every element of the Clifford group you can uniquely associate to a map. So if I have a S belonging to the Clifford group, say CPN, then this thing you can uniquely associate to a map, I guess I'll write TS, which acts on my vector space fp2 to the n, fp2 to the n, such that when I look at my symplectic form for any two elements, it's preserved. And this thing is called, I should probably start using red for everything. How do I change my color back? What's happened here? This thing here is called a symplectomorphism. And if you look at a graph, so if you look at the graph of this symplectomorphism, so if you recall that the graph of a function from a set x to y is the subset, let's say, something like gamma of f, the subset of x times y such that, or defined to be pairs x f of x. I've got these a bit different. Pairs x f of x for each x belonging to x. If you now look at the graph of this symplectomorphism, so I'm looking at now, instead of an f, a symplectomorphism, maybe t, from fp2 to the n to fp2 to the n, then the graph of this in fp2 to the n times fp2 to the n is also, and this is a key point, a Lagrangian subspace of that bigger space, the direct sum of the domain and the codomain of my symplectomorphism, which are the same space in this case. And finally, we can actually also capture post-selection in this stabilizer theory. So it turns out, and this is at least in the stabilizer state or stabilizer subgroup picture, very much, I mean, it's not obvious to me that this should be true, at least at first glance, that if I have a stabilizer state, maybe I should write this in the group notation, on, say, a tensor product of two qubit Hilbert spaces and another stabilizer state just on H, then the projection of this thing, or the post-selection of this thing, in the following way, so where I post-select G on the first subsystem of S, this is still stabilizer, which means that there is, say, another stabilizer group H that you can find that uniquely characterizes this state in the same way as any stabilizer state. But it's really not clear how this comes about, at least in this picture for me. Can we move things in this? Yes. So what you can do is take this Lagrangian picture, Lagrangian subspaces. And so if you recall, every stabilizer state S here is associated to some Lagrangian LS in the symplectic vector space, say, on n qubits. And similarly, this G is going to be associated to a different Lagrangian subspace on some FP, maybe I should note this, M plus N, and this one is 2M. Where am I going with this? Yes, so now what I can do is I can view these things as actually subspaces, just as the graph of the function gamma of t was a subspace of fp2 to the n plus fp2 to the n. I'm going to view these things as functions from some essentially trivial symplectic vector space to fp2 to the m plus n. And this thing I will view as a function, or as a relation, in this case, 2 to the m plus n to this essentially trivial vector space. And if I do the relational composition of these two linear relations, or relations from the trivial symplectic vector space to my symplectic vector space for the whole system, and then compose with the identity relation summed with the relation for the projection I want to do, then I will also get a Lagrangian relation, or sorry, a Lagrangian subspace. But now of f to the p, 2 to the n, which is the sort of remaining unprojected, unpost-selected qubits in my system. And this is precisely going to be in correspondence with the subgroup H here, following this sort of correspondence that we established a couple of slides ago between stabilizer subgroup states and Lagrangian subspaces. So if you put all of this together, you can define a compositional version, or you can give a compositional definition of the stabilizer theory in the following way. There is a category, which in this case is a specific kind of category called a prop, where the objects of this category, I haven't written down, the objects are just going to be natural numbers. The morphisms, or the arrows in the category, are Lagrangian, are affine, let's forget the affine part for now, are going to be Lagrangian relations from, so if I'm looking at arrows from m to n, then I'm looking at Lagrangian relations f from fp to f2 to the n, which really I'm thinking of as what the color, subspaces of fp2 to the n plus fp2 to the n. The composition is given by relational composition, and there's a monoidal structure in this category, which is just taking the direct sum of the relations. Then there is an equivalence, or a projective equivalence, because we don't have enough scalars in this theory, between the stabilizer theory, or at least the Clifford fragment of quantum mechanics, and this category of Lagrangian relations. The affine part of this here, oops, is a little bit trickier to explain. The idea is that if we go back to this stabilizer group picture all the way up here, this symplectic vector space picture here doesn't take account of any of the phases that you can generate. So when you look at elements of an arbitrary element of the Pauli group is going to take the form e to the I 2 pi p over 2 pi p x, say x a z b. And the symplectic vector space picture doesn't capture this phase here. So you need to add some additional information back in. And this is precisely captured by this notion that instead of looking at linear Lagrangian relations, you look at affine Lagrangian relations. That is, instead of looking at linear subspaces here, you look at affine subspaces of this linear. But it doesn't really change anything else. Okay, so all of this is just to say this category affine Lagrangian relations over this finite field FP precisely captures the stabilizer theory. And in fact, we know how to draw diagrams for this. This is what we did with Titouan Cole in this article, Graphical Symplectic Algebra, that I presented a couple of months ago. So affine Lagrangian relations admit a diagrammatic language, which is very similar to ZX in terms of phased spiders, where the phases here correspond to a vector in, here I'm working over an arbitrary field, but really we can just think of FP to the K times, whoops, a symmetric matrix X of dimension K over that field FP. I'm going to sort of gloss over the fact that this is symmetric, and I'm not really going to explain what these things mean exactly. But the upshot is that we can give, oh, sorry, and here we have what we call matrix arrows labeled by just an arbitrary matrix now. Z is just an arbitrary matrix. from M to N. Oops. Let me scroll, there we go. So I'm going to gloss over the interpretation of these things, but because it's a little bit tricky to give and there's not enough time in this talk, I'm going to get to the Gaussians bit. If you really want to know that, go and watch the previous talk I gave on this stuff. But all of these things interpret to affine Lagrangian relations over this finite field Fp. And we can give a fairly simple rewrite theory for these things, which is complete for this category of affine Lagrangian relations, and therefore for the stabilizer theory. And once again, I'm not really going to go into the details of this equational theory. I've already given a talk on this. Really, this talk is more about the semantics of the Gaussian subtheory rather than where the diagrams come from exactly. Cool. Are there any questions about what I've just said before I move on to the Gaussian stuff?
I don't suppose you want to give an interpretation of these diagrams. Like the generators.
Sorry, a what?
I don't suppose you want to write down the interpretation of the generators.
No, because in order to do so, I either have to introduce a lot of terminology or write a very long equation that won't mean anything to you.
Okay, okay, fair enough.
Yeah. Yeah, and I don't really have time for that. Yeah, no, I don't really want to get the interpretation. Trust me, it works, is the answer. Cool. So, Gaussian quantum mechanics. And before I can tell you about how the previous slides apply to the Gaussian case, I really need to give you the briefest overview of continuous variable quantum computing of all time. So in continuous variable quantum computing, instead of working in finite dimensional spaces, you work with an infinite dimensional space. And the reason for this is that if you consider a quantum particle in this case in one-dimensional free space, that is, it's just a point particle that can move left and right along some real line with some given momentum, then the state space of such a quantum particle can be taken to be the Hilbert space of complex square integrable functions. And what that is the elements of this Hilbert space are functions from the real numbers into the complex numbers, such that the integral of the absolute value squared of this function is bounded. It's not infinite. Now, this space comes equipped with position and momentum operators, which I've given here. Position corresponds to sort of multiplying by the argument of the function. And momentum corresponds to differentiating that function with respect to its argument and multiplying by the imaginary unit. If you do a little bit of algebra, it's not too hard to convince yourself, at least if you're hand waving a little bit, and in fact, I should add, I'm hand waving a lot here by just assuming that these things are everywhere defined. If in general, and well, it's not, these operators are not well defined on the whole Hilbert space, but don't worry about those details. They're sort of properly taken care of in the article and sort of boring to go into here. If you do a little bit of algebra, it's not too hard to convince yourself that these things are self-adjoint operators, and so in particular they correspond to observables on your Hilbert space. It also comes equipped with displacement operators, which really they're typically called displacement operators, but if quantum computing had come before quantum physics, then we might really call these Pauli operators. And they're defined in a very analogous way, except for now we're working with the sort of coefficients rather than basis states. The x Pauli or displacement acts as a translation with respect to the argument, and the z Pauli operator is still multiplication by a complex phase. And you can actually obtain these things from the position and momentum operators in the following way. So this one is ISP, and this one is exponential of ITQ. And this, proving this fact is a sort of standard exercise in most textbooks on quantum physics, that the momentum operator is a generator of translations. Cool. Now this is a definition of the Hilbert space. Gaussian quantum mechanics is a fragment of continuous variable quantum computation, just like the stabilizer theory is a fragment of finite dimensional quantum theory. And I'm going to give you at first the sort of concrete definition of what the Gaussian theory is, but this is perhaps not the most important part of the talk. The point is just, we have this subset of states called Gaussian states. They have representation in Hilbert space, which is something like a Gaussian, with the difference that this matrix phi here is imaginary and not necessarily positive. So there's some minor differences. But the point is that these things have Gaussian measurement statistics for the Q and P observables from the previous slide. And then, just like in the stabilizer theory, we can give a definition essentially, which is just, we say that a unitary acting on the Hilbert space is Gaussian if it maps Gaussian states to Gaussian states. And it turns out that there's a lot of these. This is not a trivial definition. And then, just like in the stabilizer case, if I post-select a Gaussian state onto a Gaussian state, then the result is still going to be a Gaussian state. Although, once again, this isn't necessarily completely obvious from the Hilbert space picture. Now, I don't know about you, but this definition doesn't really tell me very much. I mean, I see a lot of Gaussian things, and most of these things, if you think about them in the right way, you can somehow reduce to a statement something like this.
Robert.
Yes.
So what is T here?
P is this momentum operator from the previous slide.
Sorry, I meant T.
D.
T.
This thing here?
No, not transpose, the thing inside the bracket. The T vector.
The T vector. T, so I suppose I should this Gaussian state here is parameterized by the choice of S, T, and this matrix phi. Here, S and T are really just translations, X and Z, that have been applied to the sort of phi state with no translation.
Thanks.
Yeah, and so you can somehow reduce all of these things to a statement like everything has Gaussian measurement statistics if you look at them in the right way. But at least that's not a very satisfying description from my perspective. So can we do better? Well, it turns out that if you want to consider the CZ stabilizer theory is very unsatisfactory. Why? Well, displacements such as, say, x of the s don't have any eigenvectors in the Hilbert space to speak of. And a simple way to see this is that because this is just a translation, if I have any state at all that has non-zero amplitude at some point on my real number line, then for it to be translationally invariant with respect to xs, is going to be impossible to normalize that state. Having said that, physicists often employ states with square quotes around them, because they're not really states, that should correspond to eigenvectors of displacements in their calculations. And so, for instance, the Dirac delta, as treated by physicists, you can think of as a function in the Hilbert space, or a state in the Hilbert space, which is stabilized by the Z operator for any x. And so it would have a stabilizer group corresponding to all of the Z operators. But as I've said, this as actual states, this statement doesn't really make any sense. So we'd like to sort of do something a little bit better. Now, Gaussian states can't have stabilizers because, as we've seen, the Paulis have no eigenvectors, but they do have something which is called a nullifier. And what a nullifier is a linear operator on my Hilbert space that maps my Gaussian state phi to the zero vector of the Hilbert space. And so, for instance, there's an important state there's an important Gaussian state, which is really just the phi e to the I x, norm of x squared up to some sort of variance factor, which is called the vacuum state. And this vacuum state is, where am I? This vacuum state is nullified by what's called the annihilation operator, which you can define algebraically as just a complex combination of q and p. Here it's q minus ip. And in fact, you can also understand these formal stabilizer states in this picture, because if phi were a state such that q is a nullifier of phi, then in fact the z operator for any s is also a sort of stabilizer for this state, or at least you can sort of try and generalize the functional calculus in this way, along this idea that this is still exponential of I s q. Okay, so in general, the nullifiers of Gaussian states are all going to be of the form of a linear combination, a complex linear combination of q and p operators. And we can ask, because of this idea that these things should really be thought of as stabilizers, it turns out that all nullifiers, where we're still thinking of these nullifiers as identified. Sorry, let me reword this again. Start over. Just like in the stabilizer theory, where we thought of stabilizers as parameterized, or Pauli operators as parameterized by a pair of elements of the symplectic vector space, I can ask the same question of the nullifiers. Given that they are a C-linear combination of qk and pk's, I can ask what the coordinates now ak and bk, in what kind of space these things live. And in fact, it turns out that if I look at the collection of all AKs and BKs corresponding to all nullifiers of a specific state, these still correspond to Lagrangian subspaces of a symplectic vector space, which is now complex. But not all possible combinations correspond to nullifiers of actual Gaussian states. And so we make this additional restriction that we only look at those that are positive, and maybe I should add definite, positive definite which is the case where I only have this strict equality. So I have just an equality defined with respect to my symplectic form that I don't want to delve into a bit more, but which gives me precisely the nullifier or the sort of spaces of nullifiers corresponding to Gaussian states. And if I drop this definiteness condition, then I'm going to get exactly the Gaussians plus these sort of formal stabilizer states. And in fact, so I can say that in the case where, warping notation a bit, in the case where I'm strictly positive, then this is going to be Gaussians. And in the case where this form vanishes, this is going to be these sort of stabilizer things, which I'm now adding back in somehow at a formally at the level of these Lagrangian relations, rather than thinking of them as elements of Hilbert space. And so now if I take a positive affine Lagrangian subspace of this complex symplectic vector space, then this Lagrangian subspace uniquely defines a Gaussian state. If I add definite, satisfying the property that for every element of my subspace, the associated operator nullifies, associated linear combination of position and momentum operators exactly nullifies my Gaussian state. And so we say that S is the nullifier space associated with the Gaussian state phi. Now, what about unitary transformations in the Gaussian theory? Well, interestingly enough, there's not really any more than in the stabilizer case. If you look at the sort of physics articles, you'll find statements along the line that every Gaussian unitary from L squared of R tensor M to L squared of R tensor M, that is sort of M particles to M particles. These are both the same M here. Is associated to a symplectomorphism. But this symplectomorphism is actually a real symplectomorphism. So it goes from R2 to the N with the corresponding symplectic form to R2 to the N. These should be N's rather than N's. But we can easily embed these real symplectomorphisms into complex ones by noting that the yellow line here at the bottom is the complexification of the bottom line. And what this really means is that elements of things down here you can think of as x plus I, y, where these are real 2 to the n things. And then symplectomorphisms will act on this just as sx plus isy. So the real symplectomorphisms are all complex symplectomorphisms as well in this way. And it turns out that the graphs of these real symplectomorphisms embedded into complex symplectomorphisms are precisely positive Lagrangian relations. And once again, these are exactly those on which the symplectic form vanishes, or this sort of, where we have this positivity condition is minimized. We're not really positive, you're just exactly equal to 0 with respect to calculating this slightly confusing linear form. And so we can do exactly the same thing as what we did in the stabilizer case by assembling all of these things together. And so we define another category of positive affine Lagrangian relations over the complex numbers, which is just the subcategory of all affine Lagrangian relations over the complex number, which are also positive with respect to this funny form. And one of the main results of the paper that we just put out is precisely that this new category of positive affine Lagrangian relations captures the nullifier theory for Gaussian quantum mechanics, but now we also have these, I shouldn't have put infinitely squeezed, these stabilizer states, which physicists often call infinitely squeezed states. And this is actually a really nice thing because the stabilizer theory is compact closed, where the Gaussian theory is absolutely not compact closed. And this whole thing of positive affine Lagrangian relations is a compact closed category that captures the nullifier theory. Sorry, is a compact closed category into which the Gaussian quantum theory embeds. And so that means that we can begin to draw string diagrams with identities like this, where I can make sense of these cups and caps, which don't make sense as Gaussian operations. And in fact, we can go a lot further than this by noting that you can actually recover this subcategory of affine Lagrangian, positive affine Lagrangian complex relations by extending real affine Lagrangian relations. So this language that I gave a few slides ago in the stabilizer case, but now over the real numbers, by a single state, which is going to be this special vacuum state I was talking about earlier, and the following equations that just say essentially that these are, these and this are parameterizations of rotations acting on this state. And so we're just asking that this vacuum state should be invariant under rotations. And then this equation is just saying something about the scalars in the language. Doesn't really have any meaningful content from the Gaussian perspective. And so we have a complete graphical language for this Gaussian theory extended by compact closure. Do I have time to speak for a little bit longer, or should I stop there?
Longer.
I didn't hear anything.
You can go longer if you want.
Okay. Okay, so just a little bit more. In fact, we can make the sound identification because this category of affine Lagrangian positive complex or positive affine Lagrangian complex relations is a subcategory of the not necessarily positive ones. We can make the identification that this vacuum state really is a element of the graphical symplectic algebra, but now of the complex numbers by identifying it with this specific state. And all of the equations of affine Lagrangian relations are now sound for this interpretation. And so we can do a demonstration. We can sort of prove the correctness of the teleportation protocol, the original teleportation protocol, as it was first formulated, where Alice has, I'm sure you've seen these kinds of things before, but I'll go through it quite briefly. Alice has now a continuous variable quantum state that she wants to share with Bob. And they share a two-mode squeeze state or a Bell state with some error epsilon in terms of like how ideal the state actually is. And she performs a Bell measurement, which is here a projection onto Pauli eigenstates. And doing some of the sort of usual manipulations that people at this which is saying that for this finite squeezing parameter epsilon, I get some error, which is described by this diagram, and is essentially saying that you're convolving your input state by some Gaussian parameterized by epsilon. The LOv-calculus is another calculus that I think we've had talks about here before. We can interpret the LOv-calculus into our language, and it allows us to extend the LOv-calculus in a sense by things like squeeze states, which were not available to the LOv-calculus. And then there is a graph-theoretic representation for pure Gaussian states, which is very similar to the graph representation for graph states for qubits or qubits. And we can embed this into the calculus in exactly the same way as you would do for those graph-theoretic representations. That is, you take the graph, you turn every vertex in the graph into an output. Labels along edges, labels along edges become these sort of parameterized boxes, and labels sort of self edges become labels of the spiders. And I think that's where I'll stop. I have a couple of more slides with some pretty pictures, but they're not essential to understand the content of the paper.
All right, thank you very much, Robert. We'll want to use the clapping emoji in Zoom to thank the speaker. All right, I have a couple of questions myself, but I'll leave it to the audience first. Anyone who has some questions for Robert? Racine, yeah, go ahead.
Can you interpret these diagrams back in LOv-r picture, the Gaussian quantum mechanics picture?
Can you interpret the diagrams back into Gaussian quantum mechanics?
Yeah.
So if you have a, where am I here? A like positive definite or a strictly positive Lagrangian relation, then you can interpret that as a state in Gaussian quantum mechanics. It's tricky in general to decide which positive Lagrangian relations correspond to actual physical operations, precisely because some of the strictly positive, the sort of vanishing ones, such as symplectomorphisms, are physical, whereas others are not. Those which are like these ones, the stabilizer states, are also vanishing, but these are not physical things. Having said that, if you start with a diagram which is a valid physical Gaussian operation or process, then the rewriting theory will preserve that of the global diagram. Locally, you might leave operations that are physical things to do, but the global diagram remains always physical.
Okay. Anyone else? Okay, I have a couple of questions. So you mentioned this thing about compact closure.
Yeah.
Yeah, I think you mentioned like the compact closure for the Gaussian states. It follows if you add these stabilizer states, these infinitely squeezed states.
Yeah.
I'm just wondering, where do you interpret those? Because they're not elements of this Hilbert space; they're more like distributions on the Hilbert space. Right? Is that your category?
So we're interpreting them for now just as Lagrangian subspaces. So it's somehow like an algebraic model for this that we're proving soundness for.
Okay, right. So if you want to do it with the actual Hilbert space, you would need to use like distributions on the Hilbert space instead of functions.
I don't think that there is a sound semantics even in terms of distributions. I think you have to go, at least not in terms of Schwartz distributions, you have to do something quite a lot more tricky to get something that works then. Precisely because it's very easy to write diagrams where you evaluate an infinitely squeezed thing on another infinitely squeezed thing. And then in the Schwartz theory, for example, this is sort of a completely forbidden thing to try and calculate. But the Lagrangian subspace picture takes care of it quite easily.
And are you doing everything modulo non-zero scalars? Like, are you completely ignoring scalars?
Yeah, so for now we have everything up to non-zero scalars. I suspect that it's ad hoc possible to track scalars in a similar way to how we did in the Z extravaganza paper, but there's some tricky things, like you have to forbid evaluating diagrams that give you infinite scalars and things like that.
So, oh yeah, Leah, go ahead.
Hello, can you hear me?
Yeah.
Okay. I guess I have two questions. One question is about the cups and caps interpreted in affine Lagrangian relations.
Yeah.
So does this mean that they're not well in what way are they not well defined for just L2 of R?
And I'm not sure how to answer the question. I suppose writing down you can map every Lagrangian subspace to a function from the real numbers to the complex ones, or at least one of the right dimension. If you look at those which correspond to Gaussian things, then you'll find that function is square integrable. And if you look at those which are not, then you'll find out that these are not sort of positive states or positive Lagrangian relations, and then you'll discover that the function you've written down is not square integrable. I think that's the easiest way to think of it.
Okay, thanks. And my second question is about I'm kind of struggling with the concept of nullifier spaces. Is it that for the cube, let's say any odd prime cube, so cubit dimension, for your stabilizers, usually you think of stabilizers as like eigenvalues and eigenstates and eigenvectors. Sorry, eigenstates and eigenvalues. But then this nullifier spaces, is it the conjugate set of that?
I'm not sure I entirely followed the end of your question, but I can give you sort of the point is that in the stabilizer theory, you think of Pauli operators as something like this, right? Where this belongs to my vector space. In the CV case, so you can do exactly the same thing. Goes to x, z, y, where this is sort of belonging to R2, say if we're just looking at one system. But because these things are really exponential of I x q and exponential of I y p, I've got it back to front, t q, and I can rewrite this whole exponential to some exponential of now x prime p plus y prime q. There's formulas for doing this. And I can think of, instead of my mapping going from xy to a Pauli operator, I'm now going to think of it instead as going from xy to just this linear combination of p's and q's. So I have, instead of a mapping from xy's into the unitary operators, I have a mapping from the xy's into just linear operators, but which are restricted to linear combinations of p's and q operators. Does that answer your question? And the nullifiers are all of this form. here. And I guess maybe one extra thing to make the link between these two things is that if you use like a functional calculus, at least a formal functional calculus, then if I look at a stabilized state phi, this is really just exponential this xp plus yq on phi, and asking that this, say, xp plus yq on phi is equal to 0. If you sort of apply the functional calculus, you can substitute the 0 into the exponential, and then you just have 1 times phi, which is phi. So this thing is going to stabilize my state phi in a formal sense.
Thanks. That helps. That helps see the connection. As opposed to what would you say is so for when omega is greater than or equal to 0, that corresponds to Gaussian. Do you have any intuition from affine Lagrangian relations as to why that's still efficiently simulable, and kind of why that is equivalent to the qubit case?
I'm not sure I understand. So you're asking about, where is it? This this positivity condition here, right?
Yeah, because let's say in the qubit case, omega equals 0 corresponds to stabilizer, but then
so this thing is you should think of this definition in two parts. We're asking both that the relation is Lagrangian in the same sense as the qubit thing. So omega equals 0, say omega of x, y is equal to 0 for all elements x, y belonging to it. But then we're also asking this additional condition of positivity, which is saying that this slightly confusing form x bar is positive or equal to 0, which is a different requirement than the commutativity or the Lagrangianity of the subspace. And it turns out to be sort of precisely the definition that you need to make in order to capture the Gaussian nullifiers. In the nullifier picture, I'm not entirely sure how to motivate that fact. There's sort of other ways in which it's clear why this should be the correct definition to make, but I didn't really have time to go into. If you think of phase space pictures, then this positivity condition is somehow saying that it is giving you a condition on covariance matrices for the distributions that are associated with these states. But yeah, I don't really have the time to explain all of that. And that's in fact how I stumbled into this definition in the first place.
okay, thank you.
So Robert, these nullifiers, it's like the generators of your Pauli matrices. Could you do something similar in the finite dimensional case with Q did? Like, could you, instead of talking about Pauli matrices, talk about their generators, or does this work just way less nicely because things are not continuous?
I think it works way less nicely, and there's not really any reason to do it. This is nice because you can do this complexification trick and get the Gaussians, but in the finite dimensional picture, there's no complexification to do it, so you're not really getting anything new out of that picture. Because really all we care about are these associations here, right? This and this. And if you're not getting anything new out of doing this red association, you might as well just do this one on the left, which is what we're doing.
And you make this distinction between sort of your Gaussian states and your maximally squeezed states.
Yeah.
Is this like a real dichotomy? Like, are things like either maximally squeezed or like physical Gaussian things?
At the level of states in the calculus, yes. At at the level of sort of general processes, things that are, say, infinitely squeezed are things that preserve the canonical commutation relations. And things that are Gaussians are things that are somehow going to spread things out more because you're convolving with Gaussians. Does that answer the question? Yeah.
Yes, I think so. But then with a morphism, like if I sort of put a cup on it so that it becomes like a bipartite state, is it then saying like it's a physical operation?
So that's
If you know, if this,
which I was answering to Razin's question, is that if I have a symplectomorphism and I turn it into a state, this thing is infinitely squeezed. Which is the slightly nasty thing. It's kind of tricky to figure out what parts of the calculus are going to be physical versus which is squeezed, because somehow this operation is infinitely squeezed in a sense, just as an operation rather than as a state. And for some reason that's fine, whereas infinite squeezing in states is not. In a sense, I feel like probably infinitely squeezed unitaries are not technically physical either. It's just they're more easy to treat mathematically and therefore taken as standard.
Right, because these are like your perfect operations where like
exactly.
Which like require infinite precision, which you don't have.
Exactly, yeah.
Yeah.
Can I add something?
Yeah.
Yeah, like if you look at Menicucci's paper when he's talking about states, like he gives a bound on the more and more squeeze you want, then it takes more and more time. So this is like some stochastic process that you can only achieve very high levels of squeezing over a long period of time. So it's like initially everything is kind of a bit random, and then in practice in the lab, and then the more time you spend trying to squeeze it, then it gets more and more squeezed. So that's kind of evidence to that effect.
So you could in principle sort of take a subcategory of the physical processes, which might be the Gaussian states together with the non-maximally squeezed transformations.
But then our completeness doesn't apply.
No,
the thing that we're thinking about, but yeah, we don't know how to do it properly at the moment.
Is your completeness proof essentially the same as what you did? Like you can do the local teleportation, pivoting, get to a normal form?
No, it's closer to if you looked at the graphical symplectic algebra paper, because it's some kind of discard, it's closer to the proof for coisotropic relations.
Or like mixed state.
Mixed state.
ZX.
Yeah. I guess,
okay, that's it from me. Are there any other questions in the audience?
Yeah, I want to ask about the at the end you mentioned you can interpret these you can interpret LOv-calculus maps in this. Like, can you say what kind of operations you can do with that? What kind of continuous variable operations can you model?
In LOv-calculus or
like in your framework, but I'm guessing that goes via the translation.
So in our calculus, we can do all symplectomorphisms, so all Gaussian unitaries. That includes, I think that's generated by passive linear optics and active squeezing. So the LOv-calculus has just passive linear optics. We add squeezing and also translations or displacements, which I don't think are in the LOv-calculus.
What is active squeezing?
So if you think of it as a unitary on L squared of R to L squared of R, it takes a function f of x and it maps it to, say, by a parameter eta, 1 over eta squared f of eta x, or maybe it should be 1 over x of eta. I can never remember which way you go, but something like this. So somehow you're taking a function which is f and then making it thinner, but more peaked.
Oh, so is this like you put the multiplier before and after a spider?
I mean, it's really just like a multiplier by eta in the calculus.
Oh, so because this f is this, oh yeah, okay, makes sense, yeah. And okay.
Maybe this should be eta minus 1. I can't remember, something like this.
And can you say what these elements are that you have on the slide?
Good question. What are these? So this is a rotation. Maybe just to say a few more words about this slide, because I did gloss over it very quickly. In the LOv-calculus, the wires are essentially laser beams. In a laser beam, there is a vertical and a horizontal polarization of light. So in fact, in our calculus, we split this laser beam into the vertical and the horizontal polarization. And then this generator here is a rotation between the vertical and the horizontal polarization. This is a cosine of theta. This is a tan of theta minus tan of theta. So this is really just, if you calculate this out, this is going to be the usual matrix representation of a rotation, where you have like cos theta, sine theta, and so on. The one down here is essentially the same thing. It's a polarizing beam splitter. And it's just doing a rotation between the vertical modes of two laser beams, or the vertical polarizations of two laser beams. This is a beam splitter, and it's also doing a rotation. For some reason in the LOv-calculus, they take the normal beam splitter to be between the sort of the horizontal polarizations, and the polarizing beam splitter to be between the vertical polarizations. I assume this is something to do with how you can decompose indexing of matrices. And then this one up here is just a phase gate. So this is saying I take a function phi and I map it to e to the I phi. Oh, maybe I should call this phi f. Gets mapped to e to the I phi f. And then these are just vacuum projections and effects.
Thanks a lot. So the beam splitter here is not the usual beam splitter that we think about. Is it like where there are two parameters about like the reflexivity and the angle?
What does the reflexivity usually do in a polarizing beam splitter? I can't remember.
I'm thinking of like the usual continuous variable beam splitter. Like it has two parameters. I can't remember off the top of my head.
No, I can't remember either, so I can't answer the question. Because I think so. If I remember correctly, you can either think of a polarizing beam splitter as a rotation, or you can think of it as having a transmittance and a reflexivity, where then you have to ask that something like the reflexivity plus the transmission squared is equal to 1, which is really saying something like cos of theta, the r is equal to cos of theta, and the t is equal to sin of theta, or something like that. And so you can recover your parameter like that. Is that what you're asking?
I think it's probably related in some way like that. Yeah. I was just wondering if there's a like easy way of seeing that. So like for example, the linear optics picture of like the Q path or like ZW, like you have W nodes on two wires, and like they're connected by the like the edges have the parameters of the Hadamard matrix.
Mm-hmm.
Like so it looks like that with cos theta and sine theta type of parameters, but
right.
Yeah, I don't know what it looks like here.
So no, we don't have like creation and annihilation operators or stuff like that.
I understand, but the mean splitter is still a Gaussian unitary, so I'm sure you have
So
a
which
diagram.
diagram exactly are you asking about?
I was thinking of the like the mean splitter they write in QPath, for example.
Right. Okay. I can't remember what it looks like. I can open that paper quickly. Yeah, because there's this thing, because it also the beams that they have is, I remember thinking about this and I can't remember what the answer was. The answer was it's the same thing, but I can't remember how. Because the beam splitter they give is like the unitary representation of the beam splitter, isn't it? But it turns out to be the same thing. It's just you have to think about it in the right way. I can't give a better answer than that at the moment because I can't remember what the right way to think about it is anymore.
That's all right. Thank you very much.